All right. Well, thank you very much. So that was a really nice introduction. And I just wanted to thank everybody for being here, and happy Father's Day to all the fathers out there. So thank you so much for inviting us. So yes, as was already said, I'm John Hershey, and I lead a research team in machine perception at Google. And Efthymios is here, and he worked with us during his internship last summer. And he also stayed with us for the fall and spring. So he's really been with us for a while now. But we had to let him go eventually to finish his PhD. So yeah, we'll be talking about self-supervised sound separation with a particular focus on on-screen sound separation versus off-screen. And there were a few other collaborators on this, and I really want to especially call out Scott Wisdom, who played a major role in these things. Sorry, I'm on the wrong. There we go. Okay, so yeah, just a quick outline. So I'll start by talking about audiovisual scene understanding from a high level, and then narrow it down. And I'll go over some recent work that we did on unsupervised separation, because it feeds into the audiovisual stuff in a big way. And then finally, Efthymios will talk about how we use that unsupervised separation in the audiovisual model that we call Audioscope. So for scene understanding in general, we're kind of driving at like general purpose open domain stuff, because if you want to train a really big model to do really well in an open domain, you need a lot of data. And the catch is that the more data that you want to use, the less you can really rely on human labels and curation of databases in a particular domain, and the more you need to just rely on robust learning methods. So a common paradigm for this kind of like, let's train a big model is, on unstructured, in the wild data, is to use some kind of cross-modal self-supervision and do representation learning, either using like contrastive learning or maybe predicting one modality for another or from another or both. And you get representations of a scene, in the form of embeddings that can match across modalities, but we can't really necessarily understand what those embeddings mean. They're not usually interpretable, especially in terms of like the individual objects and sounds. And we know that if you get a random video from YouTube, there's going to be a lot of different sounds in them, a lot of different objects, maybe a lot of off-screen objects and sounds too, or objects making sounds off-screen. So this is more like what I would be interested in seeing. What we really want is something that disentangles what's happening inside the network. Or we want a network, in other words, that has latent variables that disentangle what's happening in the world. To understand a scene is to sort of know about its moving parts. What are the individual objects and sounds? How do they relate to each other? And how do they relate to, descriptions and words in text that might be describing them? And so the rest of this talk is about how we can try to infer the individual sounds as latent variables and associate them with the corresponding video objects, using sort of like the minimum of data curation and labeling that we can possibly use, so that we can take advantage of the mountain of data that is right in front of us. This is kind of like geared towards a CVPR audience. So like, there's a lot of vision tasks that, this is maybe excessive because I know you guys know a lot about sound separation over here. But anyway, like, there's different types of sound separation. So like speech enhancement is sort of like, semantic segmentation by analogy. You want to separate the speech from like all the other sounds. So there's one class versus another class. But general sound separation is more like instance separation, because like there aren't really classes, and you can't really use class information anyway, because if there's multiple instances of the same thing, you still want to separate them. And so that's the domain that we're sort of thinking about and operating in, like multiple instance, general, domain free, like class free separation. But the analogy, I think, is not quite great with segmentation, because sound is not like vision in the sense that objects occupy a region of pixels, and like one pixel sort of belongs to one object, and it's sort of a contiguous region. So a better analogy would be transparency. if we take two scenes and mix them together, it's sort of like, imagine you're standing in front of a store window and you're looking through it and you see the stuff on the inside, and you also see the reflection of the stuff on the outside. And now every pixel belongs to two different scenes. And that's more like what sound separation is like, because each pixel has contributions from multiple signals. And so it's really an ill-posed problem. There are more unknown variables than there are observations to infer. It's a little bit better in the spectrum domain, but as you can see, it's still pretty bad. But this is a paradigm that's been working for quite a while, is to do supervised training. Like, again, going back to vision, like you can get humans to label the boundaries of objects and get training data for supervised segmentation, but you just can't do that with audio. Fortunately, there's another way that's even easier in a way. If you get a curated set of individual sounds, you can mix them together, create a mixer, and then train the network to separate them back apart. In the open domain setting, like there's no particular order to the sounds. They can be of the same class, different classes. So when the network outputs some sounds, you have to match them up with the reference the best you can. And that's what permutation and variant training is about. We get the estimated sources that are produced from the network, and then we decide what is the best assignment of those sources to the reference sources by finding the best permutation. Now, in some cases, we may have more estimated sources than actual references. Like if we want to handle variable numbers of sources, we may have a few references for the sources that exist, and then we just have zeros for the ones that don't exist, and we have to match up the zeros as well. So like our basic strategy for variable number of sources here is just going to be have a bank of outputs and let the network assign zeros to the extra outputs. Okay, so yeah, supervised separation works great, and there's been a lot of great success. I mean, I think over the years, like it's kind of blown me away. Like we created this speech separation database, 5 or 6 years ago, and then people like drove the performance through the roof to the point where I wouldn't even trust the numbers anymore. they're just too good. But like it's a good paradigm and it works well. What are the problems with it? Well, one thing is like you can make synthetic data, but how do you know it matches your real deployment data? Like what if there's different kinds of reverb in the deployment data or a different distribution of sounds in the background? Like how are you going to match that? You can't really observe that distribution, and synthesizing, we use very simplistic methods to synthesize reverberation and stuff. Like the real physics is actually hard to simulate. You need finite element methods and stuff like that. So anyway, there's a lot of mismatch. But I think for this talk, it's really more about, can we cover the wide distribution of sounds that you would get if you analyzed a massive, hundreds of millions of videos, like all the sounds that occur in there? Can we cover that with curated databases of isolated sounds? I don't think so. There's some sounds just don't occur in isolation. You think about sports sounds, like there's an audience, they're always making noise. So it just never happens that you get like clean sounds of all of the things that happen in sports, for example. So like to find enough data, we have to open it up and use unsupervised learning. That's basically what we're saying. So how do we do that? We recently discovered a way to do that. So this is really good news. Unsupervised sound separation can be done with something we call mixer invariant training. And it's a really simple trick. So suppose that all you have to train on is mixers. What can you do? Well, you can mix them together, and you could run them through a separation model. I'm not getting into the details of the model, but say it has a number of outputs. And then you have to match these sources back with those mixers. So we can assign each source to one of the mixers. And then for each mixer, we can add together all of the sources that were assigned to it. And then our loss is going to be the reconstruction error between the sum of all of the estimated sources that were assigned to it and the mixer. And that's it. And amazingly, this just works. What are the benefits? So it's versatile. You can use it for different tasks, and we've tried it with speech enhancement, speech separation, and you can use it for domain adaptation. So like if you train using synthetic data and you want to adapt to real world data, it only takes a little bit of real world data with unsupervised training to shift your model over to the new domain. And so I have an experiment to show for that. And then of course here we're really talking about very large amounts of unlabeled data? Can we get interesting models from that? And really, for audiovisual purposes, one way to think of it is, in vision, you've got this handy field over which you can apply attention, right? You have a comment, and you've got embeddings for each location, and attention sort of selects the objects by selecting the location. But you don't have that for audio. So what are you going to do? There's this catch-22. You have to separate first, and then you have it, right? So it can provide a basis for attention over sources. So here's just a quick experiment just to show the domain adaptation thing, because I think this is kind of neat. So like you train supervised on reverbs, that's the first bar, and you get a certain performance in terms of improvement of SNR on reverberant data. Okay, so now you train supervised without reverb, so it's a mismatch condition, and performance suffers, like you go down to 4 dB. Now we do the same experiment, but we just add 10% of unsupervised training on the reverberant data. And boom, it goes right back up to where it started. So this means that you could deploy a system, get a little bit of user data, train without ever looking at that data because it's unsupervised. No human has to look at it, and recover full domain adaptation. So I think this is kind of a game changer for real systems that would go into deployment. And you can do fun things with it too. So this is an example of, what if we take a giant database of field recordings of birds in the wild, really in the wild, literally. And we just use Mixit to train unsupervised on that. So what do we get? And this is some of the cleanest separation I've heard. So here's the mixture. So I'm told that's a robin in the front and center. I'm no ornithologist. But anyway, so here's the background, including like wind noise and a little bit of music, I guess. Now here we only asked for 4 sources out, so the model didn't even have room to separate out all those little sources in the background. I don't know how well it would have done because they're pretty deep in there. Okay, so what is that? I don't know. This is where classes aren't going to help, right? This is tape recorder buttons being pressed. I don't know. You tell me. Okay, so that one is a bird, but it's like a distant bird with reverberation on it. And then the one that's front and center is like dry, like there's much less reverberation. So we think that actually reverberation is one of the cues it learns to separate things, and I think that's kind of really interesting, actually. So, and for the just more universal case where we don't even have a domain like field recordings of birds, like we can use this in general and train it on like I guess this is trained on YFCC 100M, just like all of the audio for the videos in there. And I'll go ahead and play this. Okay, so welcome to real data. It's kind of a mess. And here's what we get out. So like some background wind, car noise, stationary noise type stuff. We get crowd noise there. And here we just get that one guy. So like apparently woo and crowd noise are 2 different things to this network because, crowd noise can be considered a texture, right? And the woo is a single source kind of. And so, but an interesting thing is we tried joining this up with classification as a loss. So we had a loss that discouraged putting different classes in different sources and tried to maximize the classification of sources. And here people, this was audio set. The audio set, according to the audio set labels, a person is a person no matter how many they're mixed with. It's just people versus not people. So when we train that way, then the yell and the people talking get put together. So it's kind of interesting. Like if you may have different tasks, and in some cases you want to do class-based separation. So you can use classification as an auxiliary loss So what does this all mean for audiovisual learning? So I guess it's a little bit of a contrast to a lot of the other methods that have been coming out. So a common strategy is locate first, right? Because we have visual detectors for faces, or we have visual detectors for musical instruments, and then condition on those things because we know we have data where the things that are making the sound are on screen, and then separate those things that are on screen. And that's because in vision the objects can be found by the location, but that's difficult to handle arbitrary objects if you don't have a detector for that weird thing that's making the noise, or silent objects that could make sound but they're just not, or things that move off screen. So with Mixit though, you have an alternative strategy. You can first separate the sounds, and then use the sounds to find which, if any, of the on-screen objects are making that sound. So in Audioscope, which is up next, we'll show how we do that and using attention to do the alignment. First, I just want to give a demo of some Audioscope outputs. So here, I chose this demo because it's kind of a non-standard sound that comes out here. So the way the input video is prepared, it's just a video from the Flickr database, and we supplement the original audio with by adding the soundtrack of a random other video to it. So we make an extra noisy video. Here's what it sounds like. So she actually whispers in the original video, but you can't hear it because there's this sound of rushing water from a kayaking video. It just obliterates everything else out. But you do hear the clunk of the broom hitting the countertop. The first version of Audioscope, which we put out in ICLR 2021, doesn't notice this. And it could be because it has only 1 frames per second of video, or because it has a very one layer attention model. But here's what it does. So it picks up the speech a little bit, just a little vocalization there, but it doesn't really get the broom handle, and it kind of lets a little bit of the noise through. And here's the improved Audioscope. Yeah, nobody can retrieve the speech because it's really buried. You'd have to synthesize it. So there are other talks that cover that, but yeah. So anyway, I just think it's really cool that this just shows that it's not using class information, because who knows what that thing is? It could be made of paper for all you know. Like it hits the counter, and it's just the fact that there's a contact there and the synchrony between that audio and video that allows it to do this. So I'm going to turn it over to Efthymios now. So I will stop sharing. He's going to jump on.
Hey. So I think I have to, you have to enable me to share my screen.
Oh, so sorry. I'll fix that.
Yeah.
Yeah, we had to split it up this way because
sorry.
The problem with playing
No,
the video.
that's my fault.
It's Efthymios.
Try now. Sorry.
Okay, cool. Thanks. So, first of all, thanks for having us here. So I'm gonna talk more about what we're doing in Audioscope. The goal is, of course, to capture any kind of sound that might appear on screen. And a conventional recipe to do so would be to train a separation system with some kind of data. But this kind of data, as John said before, might be not easy or nearly impossible to gather. So Audioscope extends on prior work by across some axes. So it requires less dependence on object detection modules. The training procedure is more robust under the variety for the classes of sounds which might appear on screen and the number of sounds. And also, most importantly, is that Audioscope is able to learn from in-the-world videos where some of those videos might not contain any on-screen sound. So our data set is based on the YFCC 100 million video collection. And we, from the first Audioscope version and the second one, we release 40,000 clips annotated for their on-screen presence. And here comes the problem. We have found that at least 26% of these videos, both for training and eval, do not contain any on-screen sound, which might be really cumbersome when you train when you train your model. So what we did in the first version is that we used an unsupervised pre-trained coincidence model on audio set, and we filter out a portion of them. So effectively, we search for videos which are more likely to contain at least one on-screen sound, but as you see here, the model was not perfect. And even after filtering, at least 10% of them did not have any on-screen sound. So briefly, the Audioscope inference and training process is this one. So we get a video with its corresponding video soundtrack. We sample a random soundtrack from the huge data collection, and we form a mixture of mixtures similar to what Mixit did. And then we let the sound separation model estimate a few sources, and for each one of those sources, we extract an audio embedding. And now we do exactly the same thing for the visual part. So now we combine those two modalities, those two embeddings, with an audiovisual attention mechanism, and then we let a classifier compute an audiovisual coincidence score per source. So now we use those scores as soft weights in front of the estimated sources to provide the on-screen estimate. So in order to train this model, we use as pseudo labels the mixed assignments that come out from the sound separation training procedure. But you can imagine that we use those mixed assignments as pseudo labels for guiding the audiovisual classifier with a multiple instance loss. But now you can imagine how much noisy those labels might be, those pseudo labels might be, because if even Mixit does its job and does it correctly, so let's say it says that the blue source corresponds to, let's say, the random soundtrack, and the red source corresponds to the video soundtrack, then there is no way Mixit knows that the red source is also on screen. So those labels are really noisy. So in the next version that we have put online the previous days, what we noticed is that the most important things are the following. First of all, we pre-trained the sound separation module, which really helps with the noisy labels provided by the Mixit assignments. Then we freeze the audio and the video embeddings, and we also extract some low-level representations for both the audio and the video modalities. And this thing also helps us avoid overfitting in the overall system. And even more importantly, we build more expressive audiovisual attention layers based on transformer architectures, as we're gonna show next. And as John said before, the Audioscope V1 had a quite simple architecture. So we extracted for each source, each estimated source, a time invariant audio representation, and we used the spatiotemporal attention where we were attending for each source at all spatiotemporal locations in the video. However, by doing so, we lost, some synchrony-based features that we could be able to extract, and the information was more class-based, and it couldn't, this model couldn't actually capture trends and characteristics between the audiovisual features. So what do we mean by more expressive attention layers? First of all, you can see here at the left that we have an audiovisual self-attention block where we concatenate the audio and the video features. And then we have a repetition of those transformer blocks, which capture any kind of dependence through space, time, and the number of sources. And we also experiment with the cross-modal attention, where we don't concatenate, but we keep the modalities separate. But what we do is that effectively we use one modality to modulate the features of the other modality. And then we do that again and again repetitively. So this joint self-attention block that we said before, it captures all of the dependencies. They're really complex mechanism, but it comes with some kind of quadratic complexity between each axis that you attend to. So we had a few problems when applying those things and training with higher frame rates because it's quite memory inefficient. So what we propose is that we can effectively separate the attention across those axes that we want to, and effectively we want to approximate the joint self-attention by first self-attending across time, and then when we concatenate, we attend across the second dimension independently. So what we do is that we can gain a huge boost in the computational complexity, as you see here, because the multiplication effectively becomes an addition, which is really important when, for example, this number is quite high. So we can do exactly the same thing with the audiovisual joint cross-model attention, where we now have two attention mechanisms. First, for the audio features, we attend across the number of sources and time, while for the spatial features, for the video features, we do across space and time. So we have another separable variation of this block, which is shown here, where we do exactly the same thing, and we gain and we get the same kind of gain for our computational complexity. And now the question becomes, okay, like if you actually replace your joint attention module with this more efficient separable attention variation, are you going to lose from the accuracy and all? And we're going to say that this is not the case. So we first evaluate Audioscope and its new version, as you see here on the left, on the same filtered evaluation data that we had in our first ICLR paper. So we see here that, first of all, the Audioscope V1 trained on filtered data is in-domain training, while with our new model, Audioscope V2, we can get much of an improvement across all of the metrics of area under the curve, on-screen sound reconstruction, and off-screen power suppression, while we train with the unfiltered data, like a more general data set. And we also say that when we replace the joint self-attention with separable attention, we still get similar results. So now what happens when we evaluate on the unfiltered eval set, which is a more demanding data set? We see here that, first of all, the first version of Audioscope completely fails because effectively it predicts 0 for all of the estimated sources. And because it was trained on the filtered data. By changing that and using a higher frame per second, we see that we can boost a little bit this performance and fix that. However, in our new model, in our new Audioscope V2 model, we perform better across the board by some significant margin, as you see here, for the on-screen sound reconstruction. And the same applies for as well for the separable attention. So I also want to play a few videos to let you understand what's happening with this new version. So we can hear the human speech and some kind of background ducks flying around.
Has a full-terminal GPA, a desire to find a cure for cancer.
So Audioscope V1 can barely capture what's happening with the speech. However, in Audioscope V2, we can hear that the speech is pretty much isolated.
Has a full-terminal GPA, a desire to find a cure for cancer.
And even more importantly is that the on-screen faces are almost not appearing on screen. So it would be really hard for any model to do something like that with 1 frame per second. So another thing that we want to see, like what happens if we flip the sound? So you're in a park and you see whatever the ducks flying around, and then you have the off-screen random background speech.
Has a four-terminal GPA, a desire to find a cure for cancer.
So by focusing on the attention map provided by V1, we see that although it kind of separates, we see that the attention is all over the place. However, in Audioscope V2, we can see and hear that it has a better performance, but also the attention captures the transient characteristics of those DACs flying around. So that's all from us. Thank you very much for attending the talk, and we would be more than happy to answer your questions.
Thank you. And I see that there's already been a lot of discussion in the chat. So if people haven't looked at that, they can take a look. John answered several questions about his work. There is now a new question from Andrew. It's he says, "Hi, great work. I'm just curious why YFCC 100M instead of audio set."
Yeah, well, so for the mixes, we've done it on both. But for this one, we have some certain limitations on what we can use Google data for internally, and you know, Google's very careful about the data. So YFCC is nice because it's just open. It has an open license.
And there's another question. And again, I'm just reading these for people who are on the live chat, on the live stream. The question is about Audioscope. Any idea why the joint AV model seems to perform better than the AV separable model? Thank you.
So the joint version is a little bit more complex, as we showed before, compared to the separable variation, which we proposed in order to avoid this kind of problem with the inefficiency. So you could think about that as, you know, like a superset of all possible functions that you can represent with the joint model compared to the separable version, which is a simpler and more efficient version.
The separable one is about 3,000 times less complexity in terms of that product space than the joint one. So it is a big difference, at least in that attention layer.
Well, thanks so much, both of you. If people have further questions, they can get in touch with the two speakers.